Hi everyone. So this used to be a lesson that I taught in class, but honestly, there's very little to understand. So I'm flipping this. Today we're going to learn about a bunch of things. You should be taking notes. You can alternatively read the book because there's very, very similar information. And then in class we will just do a little bit of work to solidify our understanding, and that will be it for this topic. The first thing that the IB wants you to understand is the difference between primary energy and secondary energy, and it's pretty straightforward. So primary energy is just energy that you get straight from nature, without any processing. So for example, the energy is stored in coal, or the energy is stored in fossil fuel, or in the wind. And then secondary energy is energy that you have already processed. So for example, if you have electric energy that you've obtained, for example, with a generator, that's secondary energy. That's pretty much it. The second thing that we need to learn about is two different concepts. One of them is called the energy density. And the idea is that if I have, for example, a bunch of coal, they contain a certain, I can burn that coal, and then when I burn this coal, I will get energy from it. Now, of course, if I, instead of burning, let's say, a cubic meter of coal, I burn a cubic meter of oil, I'm going to also get energy, but I'm going to get a different amount of energy. And the same goes, well, if I get like 1 kilogram of uranium and I get it to fuse, then I'm going to get a different amount of energy. So each different substance has a different energy density. So of course we define energy density as the energy per unit volume that a substance will have. And of course the units will be joules per meter cubed. On the other hand, we have a related quantity, which is, well, okay, what if I'm not interested in how much energy I get for a certain amount of volume, but for a certain amount of mass? So for example, what happens if I burn 1 kilogram of coal, or I burn 1 kilogram of oil? Well, in this case, we don't talk about the energy density, but we talk about the specific energy. And the specific energy is very, very similar to the energy density, but instead of telling me the energy per unit volume, it tells me the energy per unit of mass. So you will take the energy, divide by the mass, and of course the energies will be joules per kilogram. Now, just so that you have an idea of how things, like how much energy a typical substance contains, I'm going to show you a little table with different energy densities for different materials. So here you can see a table with different energy densities, and just so that you notice, look at uranium, an energy density of 10 to the 18 joules per cubic meter, and compare it to the next best thing, which would be coal. There's a difference of 10 to the 8. That's 100 million times more than coal. That's why we use uranium, because uranium has huge energy density, which means that we can extract vast amounts of energy from a very, very, very small piece of material. Of course, there's other problems, but it is just so vastly more energetic than anything else that it makes it very hard to avoid. Now, this thing you should already have done in the IGCSE, and hopefully you remember, and I'm pretty sure you've done this like 30 times since grade 5. But the basic idea is that there's two types of energy. One type is renewable, the other one's non-renewable. And renewable energy basically is energy that can be produced faster than it's used. So for example, biodiesel is renewable because you can make it faster than you deplete it. Then, if a type of energy cannot be produced faster than it's used, so for example oil, then it's not renewable, in the sense that we are running out of it faster than it takes for us to get new reserves again. That's pretty much it. Okay, so how do we obtain secondary energy from primary energy? Well, the answer is remarkably similar all the time, and again, we've done this in the IGCSE, so this should only be a little review. The idea is always the same. We heat water. So Basically, we have some sort of furnace or boiler or whatever you want to call it, where you burn stuff. We'll just call it a boiler because we're boiling water in it. What do you burn? Well, you could burn coal, you could burn oil, anything you want, any fossil fuel, for example. And in here you burn the oil, and you have these little pipes. Okay, that's supposed to be a pipe. I don't know. I can't really draw. But these pipes are full of water. So in here, there's a bunch of water. And of course, you heat it up and the water boils. So what you do then is you send the water through a turbine. And, well, I don't really know how to draw a turbine. And I don't know. Let's just draw it like this. Basically, a turbine is like a mill, right? Like a windmill. So it's just something that spins when steam goes through it. So basically, we have a turbine that will spin, and then this thing will spin a magnet. And we will learn about this later on, but hopefully you remember from the IGCSE that when you spin a magnet inside a coil, so this is supposed to be a coil of wire. So when you spin a magnet inside a coil of wire, it generates electricity. Then once you have electricity, you run it through a transformer to get the voltage up and the current down so that you waste less energy, and then you can send that to people's houses. So the basic idea is always the same. Heat up water until it boils, then use the steam to move a turbine that moves a magnet inside a coil, and then you get energy. These things have names. So for example, this magnet inside a coil generates electricity, so we call it a generator. Very original name. Of course, once you've used the steam to move the turbine, you don't want to just lose the steam. Basically, what you want to do is get back all of your steam so that you can use it again and boil it again. And to do that, what you do is you run the steam through this pipe that you've put somewhere cold. And then what the water does is it condenses, right? It condenses and forms water again. So of course this thing is called a condenser because it condenses the water back. And the basic idea is that you keep reusing the same water over and over again, where you just simply boil it, use the steam to run a turbine, and then you condense it, and so on and so on and so on. And every fossil fuel central runs in the same way. Coal, petrol, whatever. In fact, nuclear centrals run in a very, very, very similar way. They also have a generator and a boiler and a condenser and so on. Now comes one of the hardest things that you will do in your entire life. They're called Sankey diagrams. And they will very likely go over your head because of their overwhelming complexity. I'm being sarcastic. Okay, so the idea is that we want some way to represent the energy losses in, for example, our power plant. So let's just say that we have a bunch of coal that has 100 joules of energy. And these should be all in percentages. So we always start with 100. Now, in this coal, what we want is to get some energy that will go to the consumers. And this energy we will display by the one that's remaining going this way. Everything that's lost will go this way. So this is the energy coming in. And then some of our energy is lost, for example, in the boiler, because, for example, some of the heat escapes through the walls. So we say, okay, let's just say that we just lost 20% of our energy in the boiler. And if we are good, this should roughly be 20% of this. In practice, you don't really have to make it exactly, but, make sure that the arrows sort of represent the percentage of energy that you're losing. So now, of course, we have less energy left. So this 100 has become an 80, so this should go over here. And now we only have 80% of the energy left here. And then, so this moves the turbine, whatnot. And then, of course, not all the energy that we put into the water is used for moving the turbine. in fact, most of it is lost in the condenser because we're cooling down the water. Let's just say we lost 40% of energy in the condenser. So let's just say that's 40, so it should be roughly twice as big as this. Okay, this is supposed to be an arrow. So we've just lost, this was the boiler, this was the condenser. So now, of course, we only have, so if we started with 100, now we'll have only 40 left, because it's minus 20, minus 40. So basically we just continue this line here, and this, and now it should look sort of like that. And then we lose some other energy, for example, at the turbine, because of sound losses. For example, because the turbine creates a little sound, and the sound carries energy away with it. Let's just say that we lose 5% of the energy, so then we make a little, very narrow arrow. Oh look, that rhymes. And then whatever's left, which turns out to be 35%, is what gets to the consumer. So this thing is called the Sankey diagram, and all it does is it illustrates, like, I had this much energy coming in, I wasted this much on this, I wasted this much on this, I wasted this much on this, and this is what's left. That's it. You are supposed to be able to draw Sankey diagrams for the main types of energy generating centrals. So fossil fuel centrals, for solar panels and whatnot. But in general, it's pretty straightforward. You need to think about, well, where will I lose the most energy and how much will I have left, roughly. And a lot of the times they'll give you the numbers, and they'll tell you where the energies are lost, if you have this in an exam. So, not overly complicated. Now, a very typical thing that they will ask you in exams, and I see this all the time, they will ask you for advantages and disadvantages of the different types of sources of energy. Because I know you'll be too lazy to actually go and check it in your book, I've already taken a photo from the book and put it here. But all of this is in your book. This is in page 318. All you need to do is either memorize this or just, it's quite common sense, right? But it's still a good idea to take a look at it. The one thing that I don't think is mentioned here, well, it is sort of mentioned here, but it's not very easy to understand, is the fact that fossil fuels, especially oil, are very, very easy to transport because you only need a pipe. And this means that there's almost no losses because, for example, if you need a truck to transport something, you need to spend energy to do that. But if you only need a pipe to transport something, then there's almost no energy wasted in taking the fuel from one place to the other. Makes it very easy to carry, very easy to place in different things, which makes it very practical. And that's why most cars use oil, because it's easy to put it in the tank, it has very high energy density, it's very easy to transport, and so on. So it's not that we use oil because we're evil and we want to destroy the planet. That's part of the reason. The other part of the reason is that it's just very convenient. It's easy to carry, it's easy to put into cars, has lots of energy density, and therefore it works pretty well. Now, in order to understand how nuclear power works, you would have to know a little bit about quantum mechanics that we haven't done yet. So I'm only going to give you a very vague overview of how things work, and then when we do quantum mechanics you will have a much better understanding of this. But the basic idea of nuclear power is that you start with an atom, normally uranium-235. Remember that uranium-235 means that it's a uranium atom with 235 nucleons, which means protons plus neutrons put together. And you hit this atom with a neutron. Remember that the symbol for neutron is 1, 0, because it's 1 neutron, 0 charge. In fact, this neutron shouldn't be very, very fast. It needs to have exactly the right speed so that it can be absorbed by this nucleus. And this nucleus gets an overdose of energy, and it has so much energy that it wants to split in two. So basically it goes and splits in two halves, normally xenon and strontium, but it could be something else. So 2 halves plus energy, which normally is in the form of gamma rays. That's the basic idea. So you get a uranium atom to absorb a neutron, and that gets it to split in two, and then the fission, because this is called fission, not to confuse with fusion, which is the opposite, releases energy. And we can use this energy to heat water, and then we take the water, we make it, move a turbine, which we use then to generate electricity in a generator. So same as always, it's just that we're using this to heat up the water. Now the thing is, uranium-235 is not very common because it's radioactive and it disintegrates. So normally in nature what you find is mostly a combination of uranium-238 and uranium-235. So, and there's way too much of this, which is not very radioactive and you cannot use for fission, and very little of this. So in order to get more of this, what you need to do is you need to basically filter this out. So you put it in this cylinder and you spin it, and so that the heavy things go to the sides and the less heavy things stay in the middle, and then you keep the things in the middle, and then now you have a higher density of this. And if you keep doing this over and over and over again, eventually you get enough density of this to be able to hold a reaction that creates energy like fast enough. And once you do that, then you can get your uranium and start a nuclear reaction. The problem with this is called uranium enrichment, is that if you are able to get uranium to a point where you can use it in a nuclear reactor, you can also get it to a point where you can use it for a nuclear bomb. And that's why people don't want, for example, Iran to have enrichment plants, because Iran says, no, but we want this to make nuclear centrals. And everybody else says, yes, but if you can make nuclear centrals, you can automatically also create nuclear weapons, and we don't want you to do that. And there's the conflict. Now, of course, getting uranium to give us enough energy is not so straightforward. Basically, what we need is to create something called a chain reaction. And the idea of a chain reaction is that we want one reaction of uranium to create more reactions of uranium. So as I said, you normally have one neutron that hits a uranium atom and splits in two. What I did not say is that apart from splitting in two and giving energy, well, this is the symbol for a photon, but you can just imagine that's just energy. It also gives two neutrons. And the good thing about this is that then if these two neutrons can be used in turn to hit another uranium atom, that then will split into two of these guys plus two neutrons, and so on and so on. So that you start with one uranium atom splitting, then you have two, then you have four, then you have eight, and so on, until there's lots and lots and lots of uranium atoms splitting, and then you have so many that they generate a substantial amount of energy. So this is called a chain reaction. This seems easy, but there's quite a few subtleties involved. The first thing is that if you have like three atoms, that's not going to work. You need at least a critical amount of atoms. So you need a minimum amount of atoms for this to work. This is called the critical mass. Critical mass. And for pure uranium-235, this is around 15 kilos. Of course, if you have 10% uranium-235, well, it's going to be 10 times more. Okay? Really, it's around 130 kilos, but you see the idea. Now, apart from this, the problem is that these two neutrons, when they come out of the uranium, they're way too fast. And because they're way too fast, they won't be absorbed by the next uranium atom. So we need to find some way to slow them down. And we do them by making them collide with surrounding atoms. Normally what we do is we put the uranium in these rods called fuel rods. So you can imagine them like this. So these are fuel rods. Fuel rods. And we submerge this in some material, usually water, but it could be graphite, for example. So let's just say that here we have water. And what this water does is it slows down the neutrons so that they can be absorbed by the next uranium atom and then maintain a chain reaction. So this water here is called a moderator, and its role is simply to slow down the neutrons so that a critical reaction may be maintained. Now there's another problem, which is if you have the moderator and the fuel rods and then you get a chain reaction going, of course this goes exponentially fast, right? So it's 2, 4, 8, 16, 32, and so on. So it's very easy for it to go out of control. And that's not a good thing, because it will melt your reactor and then you will have something like Chernobyl. So you need to find some way of keeping it from going out of control. And for that you need something called the control rods. And the control rods normally contain uranium-238, and what they do is they absorb neutrons so that they cannot be used to create further reactions. So the idea is you put like some thermometer here to find the temperature of the water. If you see that things are getting too hot, then you put the control rods in, they absorb a bunch of neutrons, and then the reaction slows down. When it's cool enough, then you lift the control rods up, and then the reaction can go again. These control rods normally have uranium-238 in them, because it's pretty good at absorbing neutrons, but it could be a different material. Finally, the next thing that you need is to use all this heat to do useful work. And to do that, you need to surround this with water, and then this water will take away the heat by turning into steam. And this water that you're surrounding this with is called, well, not the water itself, but the device where you put the water is called a heat exchanger, because it exchanges the heat between your reactor and the water that you're going to use for steam. So in the heat exchanger, the water turns to steam, and then you can use the steam in order to move a turbine, in order to get a generator to produce electricity. Alright, so just like before, here's the list of advantages and disadvantages. We've discussed most of them. As I said, the nuclear power has really huge energy density. There's actually quite a lot, and of course, when you have a nuclear reaction going on, there's no greenhouse gases going out. There's no CO2. There's no methane. Nothing. So in this sense, it's very good for the environment. Of course, the problem is that at the end, you have waste products, normally uranium-238, which are radioactive, and then you need to get rid of. People say, oh, you should put them in the sun. No, you shouldn't put them in the sun, because if you put this in a rocket, and 1 out of every 10 rockets blows up, you see the problem, right? Here's a rocket full of radioactive material, 1 out of 10 blows up, and you can understand what the consequences are. So normally what we do is we put these in huge lead containers, and we either bury them very deep or we put them in the sea. People say that this is really what we're doing, is we're outsourcing the costs of nuclear power to future generations who will have to deal with all of our nuclear waste. And this is definitely a possibility, that eventually the radioactivity leaks, and then that future generations have to actually deal with our radioactive waste. Of course, if something goes wrong, then things get really bad, like it happened in Chernobyl. The problem is not that it's going to explode as a nuclear bomb. That cannot happen, because there's not enough density of radioactive atoms. But the problem is that it may leak radioactive substances to the outside, and that is what may cause then later all sorts of problems, and is what happened in Chernobyl. Then there's another thing, which is that getting uranium out of the mines is complicated, because uranium is radioactive. It can seep into the air, so of course you can't breathe it. But another way that you can do is, well, ventilate things very well, but then you're sending the uranium into the atmosphere. So there's no perfect solution for mining uranium out. And of course, as I said before, if you have a uranium enrichment facility, this means that you can use it also to produce nuclear weapons. And nobody wants that. Right, so now we're going to talk about some renewable energy sources. So first, of course, everybody thinks about solar power. There's two types of solar power. One is the solar panel or solar heating panel. And a solar heating panel is just something that transforms sunlight into heat. So basically, it's just you see those in China a lot, but basically you have this it's a black, very black surface, and with a little deposit of water on top. And what that does is it basically just heats water, and it's very, very efficient at doing so. And nowadays, many houses have that. In Germany, for example, it's very, very common. I have one in my house. The problem with this is that, of course, you can only use it for heating up water, which is not ideal. But they're very cheap to put on the roof, and they're very efficient, so they work relatively well. The other option is to use photovoltaic cells. And these are the ones that you are most used to seeing when, I'm guessing, when you drive in your car around Germany, because it's full everywhere. So a photovoltaic cell, what it does is it transforms solar energy into electrical energy. They're not very efficient. Right now they're at an efficiency of around 30%, which is not great. But they're getting better every year, and they're getting cheaper every year. So even though you will discuss the advantages later on, it is not true that the initial costs are so high anymore. It's getting cheaper and cheaper and cheaper and cheaper to install these things, and people estimate that in 10 years' time they'll be dirt cheap to install. So we are on the verge, I think, of a little revolution regarding photovoltaic cells. Anyway, the basic idea is this basically you have a material, and you don't need to know this, but just so that you have an idea. You have two semiconductors. One of them really likes to have electrons in, and the other one really wants to get rid of them. So when light hits them, electrons from one go to the other, and it creates a potential difference. And then you can use this potential difference to do work. That's pretty much it. It's just, of course, the problem is that this only works during the day. And if we had a great way to store energy for the night, that would be brilliant, but we don't, because our battery technology is crap right now. Which means that you need some sort of alternative power source for the night. And that's where nuclear centrals come and so on. And that's why people say that so far photovoltaic cells are not a viable alternative for our future for our energy consumption, because you cannot use them at night, and there's no way to cheaply store the electricity. This may change in the future when somebody comes up with decent battery technology, but so far our battery technology has been abysmally bad. As you can, if you have a mobile phone, you're perfectly aware of this, because you run out of battery in a day. And again, here are the advantages and disadvantages. So of course, it's free in the sense that it comes straight from the sun. What's not free is the panel. Yeah, you're not gonna run out of it unless you wait for the sun to die out. It's clean, but it only works during the day. If it's cloudy, that's bad. It doesn't give a lot of electricity. Needs large areas to be installed. Though this is getting better, and the initial costs are pretty high. Again, even though this is getting better every year, like. Costs are going down by around 10% per year, which is really, really good. Now, the next type of power we will consider is hydroelectric. And of course, we also did this in the IGCSE, but now we're going to do a little bit of math. Yay! Because I don't know if you've noticed, but we've done exactly 0 math so far. I told you, this is the easiest topic by far. Anyway, let's just say I have a dam, right? And the dam has a certain height. And the idea is that I can use the potential energy stored in the water on top, which is here, in order to move a turbine that will move a generator that will create electricity. So, same thing as always. And I would like to know what things, on what does the amount of energy that I can get from this guy depend. In fact, what I want to know is the power, right? I want to know the energy per second that I can get with a certain dam. Okay, so well, let's just say that I have this water is flowing down and going this way. Well, the power is the energy per unit time. So let's just say that I have a mass m flowing down every second. So the power that I have will be, well, the energy that my mass had, which is mgh, because it's just the potential energy, mgh over the time, right? And now, instead of writing the mass, I'm just going to say, well, but this mass depends on the volume of water. So let's just say that this has a certain volume V. The mass will be the density of water, rho. Remember, this is a letter rho for density, times the volume of water. So I can just write rho V G H over T. And then I can be a little fancier and say, okay, well, how about I take V over T, and this is the volume that flows per second. And I'm going to call this the volume flow rate, because it's the rate at which the volume flows down, and call it Q. So I'm going to take this thing, V over T, and I'm going to call it big Q. I don't know why it's called big Q, but it's called big Q. So then I have that the power is then the density of the water times the volume flow rate times G times H. And that gives me the power that a hydroelectric central will produce. And as you can see, the more volume flow rate there is, so the faster the water flows, the better. And of course, the higher the dam, the better. That makes perfect sense. You're not going to change the constant of the acceleration of gravity, and you're also not going to change the density of the water. So basically, these two things are what determines the power delivered by a hydroelectric dam. So you want to make it as high as possible and make the water flow as fast as possible. What some people do is they pump water up during the day so that they can use hydroelectric power during night. So for example, imagine that I have a coal station and I wish to store some of the power, or because, for example, people are not using enough electricity, so I have some spare power. Well, I use that to pump water up a certain slope, and then at night when people do need electricity, I can use this water to generate electricity. This is called a pumped storage system. And it's a possible alternative to storing electricity in batteries. You can just store your energy in the potential energy of water that you pump up. It's not as convenient as having a bunch of batteries, but since our batteries are crap, then second best thing. And as always, here are the advantages and disadvantages that you need to know. So it's free in the sense that water flows for free. It's not free in the sense that you need to install a dam, which is extremely expensive. So inexhaustible in the sense that as long as it doesn't stop raining, you're okay, and it's pretty clean. However, if there's no river nearby, you can't use this. So that's a disadvantage, of course. This is not great for the environment. When you have enough dams, you can severely damage the ecosystem of a river, and it's really expensive to set up. I would say way, way, way more than solar panels. Of course, the amount of energy you can get from this is much more than solar panels, but it's very hard to set up. Okay, and the last thing we're going to take a look at is wind power. And wind power, we all know how it works, right? You've seen it all over Germany too. You have this huge windmill, and wind blows, thing moves a turbine, generator, electricity. It all works in the same way. So what are the subtleties of this thing? Well, the first thing is that these things are optimized for certain wind speeds, the average wind speed. So let's just say the typical wind speeds, 60 to 14 meters per second. Now, in practice, though, sometimes you have much stronger winds that can damage your things. So you need to design these things so that they're not going to break when there's much stronger wind. The other thing is, of course, you don't really take... So this wind carries energy in the form of kinetic energy of the wind particles. And ideally, you would take it all, right? So there's wind coming in, and then this takes all the energy, and there's nothing coming out. of course that doesn't happen. What really does happen is that this only uses a certain percentage of the energy, and quite a substantial amount of wind just goes out. In fact, the efficiency of these things is around 30%, which again is not great, but better than nothing. Which means that, of course, some of the wind comes in, and then 70% is actually just lost. In fact, what happens is that if you have many windmills placed around each other, because each one of them disturbs the wind after them, what happens is that the next windmill, so when the wind is coming in this way, right, but this guy disturbs the wind and makes it go like this, makes it turbulent, then these guys will get less energy from the wind than this guy did because of that. So you need to separate them quite a bit if you want to avoid this effect. And this, again, reduces efficiency and drives costs up because you need more area in order to install these windmills. And now for a little bit of math, because it's always fun to do some math. So imagine that we want to know roughly how much power a wind generator can generate. Okay, well, the way we do this is, as always, we model things crappily, and then we simply adjust for efficiency. So let's say here's my windmill, and I can model this as simply like a circle with radius r. And what I say is, well, let's just assume that this circle with radius r takes all the energy from the air that was here. It's not going to take all of it, but then if I just find what it would take if it took it all, then I just say, well, it's actually 30% of that, and then I'm done, right? Okay. Well, how do I find out the energy that the air carries? Well, if it's kinetic energy, it's given by 1/2 of mv squared. V is simply the speed of the wind, so that I have that. M will depend on the density of air and the volume of air. Okay, so let's just say, well, I'm going to make a little cylinder here. This cylinder will have a certain area A, which is, of course, the same area as my windmill. And this length here, well, let's just say in a certain time t, there will be, this thing will move at a distance v times t, right? So this is the speed of the wind, and this is the time that it takes. So in the time t, this has moved this much. So in a time t, this much wind will have gone through my windmill, and therefore the energy will have gone to the windmill and into electricity. Okay, great. So therefore the volume of this thing is just the area times the length, so it's just A times Vt, right? And of course the density of air, it was just going to be rho, because it's always rho. Okay, so what is the mass then? Well, mass is just density times volume, so therefore the energy that goes through here in a time t is just going to be 1/2 of mv squared, and m is just rho times the volume, and then the volume we just said is AVT. So we have 1/2 of rho times AVT times v squared. Great. And now we're done. Now what we want to know, as always, is the energy per unit time, so which is the power. So energy per unit time, which is 1/2 of rho A. Now notice that there's a v here and there's a v squared here. So v times v squared is v3. v3 times t, and then divided by t. And then you'll notice that there's a t that cancels out, and therefore the power delivered by a windmill is 1/2 of rho A v cubed. And this is the second equation that we will need in this topic. And that's pretty much it. So we're done. Here are the advantages and disadvantages. It's always the same thing. Free, inexhaustible, clean. Disadvantages depending on where you put it. Some people don't like the way it looks. Some people don't like that it makes noise. And actually some people complain that it kills birds. You can't make everybody happy. But that is pretty much it. So as you can see, it's just a very exhaustive list of all the types of energy. You just need to know what their advantages and disadvantages is. Problems are basically just conversion factors, and when you come to class, I will give you an example of an exam problem so that you can see how I would go about doing these things using conversion factors so that you can do them in one line. They are all the same. It's 90% common sense and 10% knowing these things, and then you should be okay. So, good luck with it. See you in class, and I hope you didn't hate this.